San Andreas has some massive plans for you all. Well, there is a time bomb waiting beneath the surface of the Earth, and it threatens the very existence of our society. Even though the San Andreas Fault has been known to threaten millions of lives for quite some time, the latest scientific findings will leave you reeling. Their studies have revealed a shocking fact about the fault's behavior, with potentially catastrophic consequences. Get ready for a mind-blowing adventure as we delve into the astonishing findings that have rocked the foundations of our planet. Let's begin. The catastrophic San Francisco earthquake and fire of April 18, 1906 brought the existence of the San Andreas Fault to widespread prominence. Yet, because of periodic displacement along the fault, this earthquake was just one of many that have occurred over the fault's lifespan of around 15 to 20 million years. The Earth's crust is broken up into plates, which have been slowly migrating across the surface of the planet for millions of years. In Western California, the San Andreas Fault marks the boundary between two of these migrating plates. Earthquakes along the fault line are caused by the northwestward movement of the Pacific Plate on the west relative to the North American Plate on the east. A complex fault system cuts through the rocks along the California coast, and the San Andreas Fault is considered the master fault. More than 800 miles long and going down at least 10 miles, the San Andreas Fault system is a massive geological feature. The fault is a complicated zone of shattered rock that can range in width from a few hundred feet to a mile. The San Andreas Fault Zone is connected to and branched by numerous other smaller faults. Little cracks, fault gouges, pulverized rock, and the occasional solid rock chunk can be seen in nearly every road cut throughout the zone. From its northern California beginnings all the way down to Cajon Pass south of San Bernardino, the San Andreas Fault is a continuous thin crack in the Earth's crust. The San Jacinto and Banning faults are two of many branching faults that extend southeast from Cajon Pass and contribute to the overall movement of the crustal plates. The term San Andreas is commonly used to refer to the northeasternmost branch of the fault zone in this area. The San Andreas Fault can be seen as a linear trough over most of its length. From above, the linear arrangement of lakes, bays, and valleys in this trough is impressive. In contrast, when viewed from below, the characteristics take on a more modest appearance. In the San Francisco Bay Area along Tamales Bay, in the Cajon and Tejon Passes, and in the Crystal Springs Reservoir area, for instance, many drivers may be unaware that they are in the San Andreas seismic zone. If you look at the landscape closely, you can spot the fault where it actually is. Several landforms, such as long, straight escarpments, narrow ridges, and small undrained ponds generated by the settlement of small blocks within the fault zone, serve as identifying features of the area. Upon passing over the fault, several stream courses take a sudden turn to the right. Chapter: How much movement do you think there has been along the fault? The San Andreas Fault causes a horizontal movement of blocks on either side of it. The block on the other side of the fault would appear to have shifted to the right if one stood on one side of the fault and peered across it. Right lateral strike slip is the geological term for this type of fault movement. Roads, fences, and rows of trees and plants that crossed the fault in the San Francisco area were offset by several yards during the 1906 earthquake, with the road at the head of Tamales Bay being displaced by almost 21 feet. Each time, the land to the west of the fault shifted northward. Only a single segment of the fault is ever the site of the sudden offset that triggers a major earthquake. A cumulative total offset develops asymmetrically over time, with most of the change occurring in successively different fault segments. After strain is built up for a century or more in the locked and tranquil portions, it is released in huge lurches, causing devastating earthquakes. Yet it appears that other sections of the fault are more able to absorb movement by steady creep, as opposed to the rapid offsets that cause devastating earthquakes. Earthquakes of the magnitude experienced on the locked parts have not occurred on the creeping sections in recorded history. Scientists estimate that the San Andreas Fault has moved at least 350 miles due to earthquakes and creep since it formed roughly 15 to 20 million years ago. A section of the fault between Tejon Pass and the Salton Sea have been studied, and the results show that geologically comparable terrains exist on different sides of the fault, now separated by 150 miles. Certain crustal blocks may have traveled through more than 20 degrees of latitude. Since the rate reflected by these ancient offsets is compatible with the rate reported during historical times, it is still hard to fathom the magnitude of the movement of the Earth's crust. Inches per year have been lost due to drifting, as measured by surveys. Chapter: What is an earthquake? Deep within the Earth, tensions are causing the crustal plates to deform. The ground bends until it reaches its breaking point, at which point it breaks and snaps into a new position. Earthquakes are caused by vibrations created during the faulting process. While some of the vibrations are extremely slow, with seconds passing between waves, others are audible. Compression waves and transverse or shear waves are the two most common types of vibrations. To distinguish them from secondary or S waves, scientists use the term primary or P to indicate that the compression waves reach their destination before any other waves. Shear or S waves are the later arriving transverse waves. The P wave of an earthquake is often first felt as a sharp thud or blast-like sensation. A swaying or rolling sensation could be felt a few seconds later, signaling the onset of the S wave. Chapter: What exactly is meant when terms such as magnitude and intensity are used to describe an earthquake? To quantify the severity of an earthquake, scientists use a scale known as magnitude. The most well-known scale for determining the magnitude of earthquakes is the Richter scale, which was developed by Charles F. Richter of the California Institute of Technology. The scale is logarithmic, thus a reading of 7 indicates a disturbance with ground motion 10 times as large as a reading of 6. An earthquake of magnitude 7 releases around 30 times as much energy as a magnitude 6 earthquake, and an earthquake of magnitude 8 releases 900 times as much energy as a magnitude 6 earthquake. The threshold below which people often feel the effects of an earthquake is a magnitude 2. Damage can be done by earthquakes with a Richter scale rating of 5 or greater. This scale has no fixed limits and has been used to measure some of the world's strongest earthquakes, including the ones that occurred on January 31, 1906, off the coast of Colombia and Ecuador, and on March 2, 1933, off the east coast of Honshu, Japan. In light of the fact that the Richter scale is inadequate for distinguishing between the greatest earthquakes, seismologists have developed a new scale called moment magnitude to provide a more precise measurement. The estimated Richter magnitude for the San Francisco earthquake is 8.3, whereas the moment magnitude is 7.7. The intensity of an earthquake is the degree to which it causes shaking. The intensity measured at different sites often decreases the distance from the earthquake's epicenter, and the modified Mercalli scale depicts the local effect or damage caused by an earthquake. Roman numerals are used to denote the intensity levels from 1 to 12. A magnitude 2 earthquake, for instance, would cause minimal harm to persons in favored locations, while a magnitude 10 earthquake would cause significant damage, especially to unreinforced masonry. The severity of an earthquake is usually determined by the local geology. Sites located on alluvium often have intensities that are 2 to 3 units higher than those on bedrock. An earthquake of magnitude 7.1 struck the Imperial Valley on May 18, 1940, along a fault that had not been previously identified. There was a quake at the Imperial Fault on November 1979 that caused a similar movement. In the 1940 earthquake, there was a right lateral strike slip of 17 feet, the largest surface displacement ever recorded. This crack unmistakably belongs to the San Andreas system. The Hayward Fault saw earthquakes in 1836 and 1868, and the San Andreas Fault experienced an earthquake in 1838 with a possible magnitude of 7 or higher. Chapter: When may the next major quake occur along the San Andreas Fault? There are stretches of the San Andreas Fault and other plate borders where major earthquakes have not happened for a very long period. Seismologists have been quite accurate in predicting when certain seismic gaps will cause major earthquakes. Severe earthquakes have occurred in the southern San Andreas Fault approximately every 150 years, according to geological research conducted during the previous 14 to 1500 years. In light of the fact that the last major earthquake on the southern San Andreas occurred in 1857, that area of the fault is viewed as a prime candidate for an upcoming quake within the next several decades. Because it has been less than a century after the devastating 1906 earthquake, the San Francisco Bay Area is at a slightly decreased risk for a major tremor. Yet, moderate-sized quakes with the capacity to cause significant damage could strike at any moment. Most likely, a major earthquake won't strike without warning. There may have been a buildup of seismicity along the fault for a number of years leading up to this quake, with some of those tremors reaching roughly a magnitude 5. Seismologists also expect to see changes in the Earth's surface before the next major earthquake, including a shortening of survey lines across the fault, changes in elevation, and effects on strain meters and wells. The Central California town of Parkfield sits on a stretch of the San Andreas Fault, where on average, a moderate-sized earthquake has occurred every 20 to 22 years for the past century and a half. This makes it an ideal location for studying earthquake prediction methods. There hasn't been a significant quake at Parkfield since 1966. A magnitude 5 or 6 earthquake is likely to strike the area before the century is up, and it could happen as soon as the early 1990s. The United States Geological Survey has installed a number of sensors in the Parkfield region and is carefully analyzing the gathered data in an effort to determine the conditions that might herald a magnitude 7.0 earthquake. Chapter: Is there something we can do about earthquakes and fault lines? Despite the fact that humans are powerless to prevent earthquakes, they can adapt to the challenges they pose. There are now 3 main defenses being developed to counter earthquake risks. Structures in earthquake zones should be made to withstand the effects of tremors. First and foremost is the evolution of building codes that emphasize the importance of considering earthquake shaking. Programs to retrofit or demolish older structures that pose a threat during earthquakes are already in motion in several areas. The strategic allocation of land is a secondary defense mechanism that can mitigate the consequences of potentially dangerous terrain. Placement of high occupancy or important buildings near the San Andreas Fault or in landslide-prone zones is not recommended. Accurate earthquake forecasting will provide the third line of defense. When this kind of foresight is available, the most dangerous structures can be evacuated in a timely manner. Since the Earthquake Hazards Reduction Act of 1977, the U.S., the Geological Survey, other federal agencies, universities, and private companies have been engaged in a massive endeavor to learn how to forecast earthquakes and analyze and mitigate their hazards. That's all we've got for the video today. We will be right back with more. Until then, don't forget to hit the like button and subscribe to our channel. Thanks for watching.